Okay, so we're all up and running on the tech side of things. So I think we're good to go for our second keynote talk of the day. So it is my honor to introduce our second keynote speaker, Professor Courtney Paquette. So Dr. Paquette is an assistant professor at McGill University, a CFAR Canada AI chair, and an active member of the Montreal Machine Learning and Optimization Group here at Mila. Dr. Paquette's research broadly focuses on designing and analyzing optimization problems, large-scale optimization problems, motivated by applications and data science. She received her PhD from the Department of Mathematics in the University of Washington and went on to do 2 postdocs, one at Lehigh University and another at University of Waterloo, where she was an NSF postdoctoral fellow. Finally, before being awarded her faculty position here at McGill, she worked as a research scientist at Google Brain here in Montreal. Dr. Paquette's elegant work shines a much needed light into the black box of high-dimensional machine learning problems, and I believe has an equally impactful potential in the field of neuroscience for helping us shed light on how the brain performs high-dimensional learning. So it's a wonderful privilege to have you here today, Dr. Paquette. The mic is now yours.
All right. Well, thank you guys for having me here. Thank you to the organizers. I haven't given an in-person talk in a long time, so bear with me as I remember exactly how to do this. I'm also not a neuroscientist at all. I came from a pure math background, so I'm a theory person. So it's going to be fun, you guys. So here we go. So to begin with, I just wanted to point out this has been joint work with people when I started at Google Brain in Montreal. So this is Fabian and Bart and Elliot. And it's expanded to include some graduate students at McGill and also to include some additional people at Google Brain like Jeffrey and Ben Adlam. Oops. Already, I'm having difficulty. All right. Okay. Oh, I have to just disappear. Well, you can't see the top. All right. So as a theoretician, there's a big problem that we have. I'm guilty of this, which is that we prove these nice results in theory, and then we go and run the algorithms, or someone runs our algorithms for us, right? And there's nothing in common with what actually happens in practice and what happens in theory. Yeah, do you know what I
feel like I could move this to the bottom, I believe.
You know? There you go.
Or to the side.
It must be a way.
Yeah, I think that this would be a problem that lots of people would have.
You can shake. I think disappears over time.
Yeah, I'm not sure there's much that I can do about that, unfortunately. Oh, there we go.
Oh, perfect. Cool. All right. See, we haven't done this in a while. All right. So there's a problem when you have theory and practice usually, right? Theoreticians prove some nice result. They're saying, hey, look, use my cool algorithm. Practical people do it. And there's nothing in common whatsoever. Right? I'm guilty of it too. All right. So what this talk is all about is at least trying to bridge a little bit of the gap between theory and practice. And so it's basically trying to explain this picture here. Okay, so what did I do? I actually took real data. So this is CFAR 10. Okay, so these are planes and cars images. All right, and I ran SGD off of it. And my goal is actually now to actually just exactly predict the behavior of SGD. Oh, go ahead.
One more minor technical issue.
Oh,
I
yeah.
guess they're having trouble picking up the sound online. So
Okay.
This is the mic here for the sound. So if you're able to hang out by the mic, that would be cool. But if
Okay.
you'd like to be able to move around
Sure.
and show people the screen, we could get one of these going.
It doesn't matter. I can stay up here. Sorry, I like to move around when I talk. Yeah, actually, can I use that? Is that possible?
This is what kind of experience. Hello, hello.
Okay, perfect. All right. Hello. Okay, great. Okay, so the goal of this talk is basically to explain this picture, which is that you actually are running SGD or some sort of stochastic algorithm on real data, and we actually want to be able to predict the exact behavior of it. Like we want to say, regardless, of the stochasticity, I can exactly tell you at any moment in time what SGD will look like, what a stochastic algorithm will look like, okay? And we can do this. What we need to have as input, for instance, is things like the eigenvalues of the covariance matrix, okay? All right, so let's hopefully we can predict the behavior. Oops. Oh no, there we go, okay. So how do we generally think of, again, I'm a theory person, of optimization? Well, here we're just trying to minimize some large finite sum of f sub I, okay? And the goal usually in optimization is to achieve some sort of iterate xk, which is nearly optimal of some form. This is how we abstractly view ML problems, okay? Now, the other thing which is really characteristic nowadays of machine learning is what I would call high dimensional. So this means not only do you have big data, you have lots of n, okay, big number of samples, you also have a huge number of features. So this is the thing which is what you're minimizing over, the space that you're minimizing over. Okay. So just to give you a sense of the scale that we're now talking about, the state-of-the-art models for language processing are in the billions of features. That D space is in the billions, okay? Actually, the current data for Google Palm that got just released is 500 billion features, okay? Huge, okay. The other thing which is kind of unusual, which I don't know how many people realize, is that if you look at sort of the state-of-the-art models for machine learning, the architectures and neural networks, they don't have what people might think of as either like much larger number of samples compared to number of features, or much more features than samples, okay? Actually, what ends up happening is that the number of samples and number of features are comparable. And these, of course, you could argue that you could solve these same problems in those other regimes, okay? But these have been optimized for performance for their networks. So what appears to be, maybe some neuroscientists have a reason out here, is that for neural networks, you have both D and N are sort of related to each other. So the number of features and number of samples are related. Okay. Okay. So how do we generally do optimization? What kind of analysis do we do on algorithms? Well, we do something called worst case complexity. So what does this mean? It means you fix a function, class of function, okay? You take an f in this class, and you compute some sort of runtime for it, say, or some sort of efficiency of the algorithm, and then you take the max over that class of functions. Okay? What's great about this is, of course, you can guarantee, no matter for what f in your class of functions, that you have a convergence. That's the guarantees that you get. What are these classes of functions? They usually just involve something like smoothness. So you just assume that you have derivatives, or you have some sort of convexity of the f. Okay? What they don't do, and what you typically see in ML, and this is kind of the point of this theory versus practice, is that if you run your algorithm and you plotted them, so these are these gray lines, and you look at this blue, which is the worst case, you see that the grays are somehow much better than the blue. Okay? And if you think about it, you would like to capture this somehow. You like to actually capture the gray, because this is what your algorithm is actually doing. Okay? So how do we actually change our analysis to somehow capture this? And what the issue is that we don't tend to use high dimensional structures. In optimization, we just ignore the fact that it's high dimension. Our bounds work regardless of if you're in dimension 2 versus dimension 1 million. Okay? So what makes high dimensions different? There's a really simple answer to this. It's just that you have more room, so you have more possibilities for your input. And as a result of this, the input which generates your worst case complexity, so the input of that function, can be really far from the typical one that you see. So if you want to get better complexity results or better understand your algorithm, you need to impose additional assumptions that capture high dimensionality. So how do you do that? So there's a way that we're going to steal from physics in a little bit, which is one way of doing that is you basically put a probability distribution on your inputs. Okay? And now, instead of computing this max, you compute the average complexity, which is that you take that max and you read the expectation being over all the inputs. And as a result of this, it tends to be more representative of your complexity, of typical behavior. You get additional things by putting probability distributions. You get variant statistics on the run times and things like that, which are also super important for algorithms. Now, despite sort of this idea, it's been around for a long time, we rarely see this in optimization nowadays. We just kind of ignore it, okay? Okay, so why don't we see this? Okay, so there's two problems. First problem is you have to be able to define what you even mean by a typical convex or typical machine learning problem. So there's one issue, okay? Now the second problem is something a little bit subtle, but what people always have had this belief of, which is that, okay, you put some probability distribution on your inputs, now whatever result you get is gonna depend highly on whatever your probability distribution is. Okay, so if you put Gaussian and you get a result, which is for Gaussian data, it only holds for Gaussian data. That's kind of the view of it. Okay, so let's address these two questions. Okay, so I'm going to start with your first one. Okay, when I was doing optimization, I was like, okay, what's the typical convex problem? To me, there's only one. It's really easy. It's least squares. Okay, right? The first one you learn, things look kind of quadratic. That's what you're always taught in school. Every function is basically a quadratic. So let's work with that. So let's look at minimizing 1/2 the norm of ax minus b. Okay, and now it's clear what we mean by inputs. Inputs here is your random matrix A. So you think of A as your data, and B as your target. It's also going to be random. Okay, and from optimization algorithm stuff, we're interested in things like when is the first time the gradient is small, because that tells us a nearly optimal point. So let's look at what happens with gradient descent and high dimensions. Okay, here's what you get. All right, so what you see actually is that for large models, so here I'm making the ratio of the number of features to number of samples kind of fixed, but I'm making them both very, very big. Okay, that the halting time, this time that the gradient starts to become small, it's actually going to converge to a deterministic value, just a single point. Okay. And it's going to be somehow independent of sort of the distribution that I put on my data. Okay, so that's what this picture is. Okay, what is this? So here's my model size. So I'm making this get bigger and bigger and bigger. What I did is that for each d, okay, I have my n fixed, and d over n, the ratio is fixed. So for each d, I generate a random matrix, I generate a random target vector, I run gradient descent, I wait till the first time that the gradient is small, and I plotted that. That's what I did, okay? And what you're seeing in the shaded region is the variance. Okay? And each of these, what I've done here is that for the different colors, they correspond to different generations of the matrix. So for instance, I generated the blue using Gaussian data, the orange is using Bernoulli, and the green is using student T. But you see, as I get larger and larger, everything is going to the exact same value, regardless of how I distributed it. Okay, why? How is that possible, right? Everything is a different distribution. Okay, so let's try and understand this in a little bit idea here. Let's look at the gradient descent algorithm, okay? And the key idea is something that we're going to steal from a long time ago, which is that for many optimization algorithms, there's actually a polynomial and what I'm going to call the Hessian. So the Hessian here is A transpose A in this matrix, A transpose A. Okay, so let's see this. What is this polynomial? Okay, let's take gradient descent. That's the easiest one. Gradient descent is just I take xk, it's equal to xk minus 1 minus the gradient. Okay, all I do is I plug in what the gradient is. The gradient for the least squares problem involves A transpose A, because I take A out, right? Get A transpose A appearing. Okay, I plug that in, I rearrange, and I get the following line. I get I minus H times xk minus 1. Okay, and then I just repeat, because I can do the same thing with xk minus 1 because it's an iterative algorithm. If I go to the second line, I get I minus h times I minus h times xk minus 2. I can go all the way back down to the initialization. And so what you get is that you can relate xk to x naught, your initialization, through this polynomial, which looks like I minus h to the k. Okay, that's kind of cool. That's the polynomial that I'm talking about in the Hessian. You can do this actually with lots of different methods. They give you different polynomials. Gradient descent the easiest of them. Okay. Okay, so what is this polynomial? So again, what we showed is that the kth iterative of an algorithm can be related to a k-degree polynomial in the matrix H. And we're like, okay, well, H is this form A transpose A. So if we go back to linear algebra, we're like, it's a polynomial, that's a positive semi-definite matrix. Well, a polynomial of a matrix can just be related to its eigenvalue. Okay, so this is actually all related to eigenvalues of the Hessian, A transpose A. And under various assumptions, what you can show is that quantities that you care about in optimization, about showing optimality, about being close, can be related directly to this polynomial in H. So for instance, if you look at the gradient at xk, you can relate it to a normalized trace of the k-degree polynomial in H. Now, if we think about it, k-degree polynomial, well, that's just involving eigenvalues, trace eigenvalues. This is really just about eigenvalues. So we need to understand, what do eigenvalues of high dimensional data matrices look like? Okay. All right. Luckily, we're saved because random matrices gives us some information. So anyone here do random matrices? No? No? Anyone? No? Okay. I'm going to convince you afterwards that random matrices are awesome. All right. So here's what happens. It's the best experiment you'll ever run. It will work exactly on your first try. It's amazing. It turns out that if you look at high dimensional random matrices, okay, that for many classes of random matrices, they share characteristics which only depend on the low moments of their entries. Okay, what do I mean? This is the idea called universality. What this is essentially the law of large numbers, or the central limit theorem for matrices. Okay, so eigenvalues, eigenvectors in high dimensions actually have concentration properties, like law of large numbers and central limit theorem. Pretty cool, right? Okay, here's the example. All right, again, you should do this experiment if you've never done it. It's really easy. It takes 2 seconds on MATLAB. All right, so if you take in entries of A, which are IID, okay, they just have mean 0 and the same variance, and you just need a finite force moment. No other distributional assumptions are needed. Okay, and what you do is you just plot the eigenvalues of A transpose A and you normalize them. You divide by N. And if you do that by first fixing this R, you'll get a distribution which looks like that. And that distribution will be fixed. The only dependence will depend on this ratio. That's it. Okay? They'll have the same distribution of eigenvalues. And this is famously known as the Marchenko-Pasteur distribution. Okay, pretty cool. You should do it. You've never done it. It's the first time you do it. It's pretty cool. If you want, you can also do the, well, there's a symmetric version which has a pretty semicircle law for its eigenvalues, but this one's not as pretty, but it's the one that shows that. Okay, so what is this data matrix really? This is because everything is IID, mean 0, right? What this is that this is like you have no information in your data at all. This is the white noise version. This is your Gaussian. If you wanted to model what noise look like in terms of eigenvalues, this is your distribution that you would choose for it. Okay? It's the white noise. Okay, so then you might say to yourself, well, how about what does real world things look like? Okay, so I'm going to follow a principle that physicists did, which is this maximum entropy principle, which is that in a real world disordered system, it's complicated, your system will look random, okay? Unless you actually prevent it from looking random, okay? So what this means really is that for a matrix, it's only interesting in ways in which it fails to look like a purely random matrix. Okay? Okay. So let's do this with some real data. Let's see what's going on. Let's take MNIST. So MNIST is the data set which has images of zeros, ones, twos. Okay, the classification. Let's form the sample covariance matrix. So the question, so I'm going to take this matrix M of data images and form MM transpose. Okay, and my question is, does this MM transpose look like a random matrix? Any guesses? No? Okay, so the first thing you do is you plot it. And this is what you get. Okay, why is this a problem? This is a problem because you have one giant eigenvalue, and the reason is that you have M has a mean in it. So you need to subtract off the mean of the data. Okay, so let's subtract off the mean of the data. Okay, even after you subtract off the mean of the data, you would get this kind of weird thing here. Well, what's going on here? Well, the reason is that you actually just have a lot of zeros, and it's because of the rank of the matrix. Okay, so let's remove those zeros a little bit. Those eigenvalues are zero because of rank. And then you end up with this. And this starts to look surprising. What you'll see here is what I've done is I put a Marchenko-Pasteur distribution on top of it. Okay. And what you can see is that for the small eigenvalue, it kind of looks like a Marchenko-Pasteur. And then you get sort of these outlier eigenvalues. And these outlier eigenvalues are things which actually are important. They're the thing which makes you be able to classify an image of zero from an image of one. Okay. But there's a lot of bulk period, which is just pure noise, pure white noise that you have. Okay. It has this Marchenko-Pasteur. Okay. This is actually really characteristics of image data sets. They almost all have this structure of something which looks like pure random noise plus some outliers. And those outliers are the things which you're most interested in. But the problem is that your optimization algorithm is going to use that bulk. Okay. Okay. So let's just finish off some of these optimization steps. What else do I need to assume? I need to assume a little bit about how I generate my B, my target. Okay. I'm just going to do it for simplicity, a generative model. So I'm assuming that my B is of the form A times some ground truth plus some noise. You don't need to, but you need something along these lines. Okay. And again, I'm always going to fix this sort of ratio of samples to noise. And then the other thing that I'm going to do is that I'm going to ensure, because I'm changing dimensions a little bit here, that I have the same signal to noise. So what it means is that as I increase N or increase D, okay, I'm not accidentally making the signal more prominent in the data or the noise more prominent. I'm going to fix that quantity. Okay, so you'll see this appear in the thing. Okay, in terms of the random matrix, what do I need about the A? All I need, I'm going to row normalize my matrix. I just need that the empirical eigenvalue distribution of my Hessian converges to this compactly supported measure. That's like the Marchenko-Pasteur. Okay, then what do you see? Okay, so we go back to our concentration or our result. We see that the gradient is basically something involving the eigenvalue. Now, if we put a random distribution on our A, we have this sort of nice little concentration of what the eigenvalues have to look like. You have some sort of form. Okay, and that's exactly what gives you these types of concentration. So you can actually show that the gradient at xk will converge to a deterministic function. You can exactly write down the exact behavior of the algorithm at xk, and it'll be this function here. What does it depend on? It depends on your algorithm through the polynomial. It depends on the eigenvalues of the Hessian, only the eigenvalues. So you get to know exactly how every eigenvalue affects the performance of your algorithm. And it depends on the signal to noise ratio. That's it. You have an exact formula for the dynamics. Kind of fun, right? And it only depends on the spectrum, right? Okay. How do you get average case complexity from this? Well, it's not so hard. Well, you have this deterministic, purely non-random thing anymore. It's concentrated. Let's call that NK. And let's just look at the first time that that quantity is less than epsilon. We can write that down. Okay. And what we're interested in is actually the halting time. That's the first time that the true gradient is less than epsilon. But because MK and the gradient are close, well, you would expect that tau epsilon is close to what you're actually interested in. That's exactly what you have. So what you're mostly interested in is just figuring out what tau epsilon is from a complexity. That will give you a better complexity result, which mimics more of what you see in high dimensions. And you can do that. And if you do that, you can run gradient descent, you can look at different algorithms, and what you'll see is that the average case is way off. We're orders of magnitude off on what we get, okay, in high dimensions. So we get gain factors of speed just by analyzing what actually happens in the high dimensional regime, the worst case. You can also do this where you have a strongly convex function. So that was the convex setting. Here's a strongly convex, and you get slightly better rates also. Okay. All right. But we're optimizers in ML. Nobody really runs gradient descent anymore. You might say, what happens if you add an extra layer of stochasticity, which is what you actually care about, which is stochastic algorithm. Okay, so now I'm going to have actually a randomness built into the actual algorithm itself. These are the things which actually run on the high dimension. Okay. Has everyone here run SGD? Stochastic? Okay, a few people. Okay. So let's look at the simplest one, which is stochastic gradient descent. So I'm again looking at a random matrix A, a random target vector B. I'm now doing stochastic gradient descent. I'm going to do the simplest one, which is just that I'm going to choose uniformly at random and f sub I, compute its gradient, and use that as a proxy instead of the full gradient. Okay. All right. Any guesses what you think will happen in high dimension? Will be like random? Noise? Anyone? We'll concentrate. There's randomness, right? Because now I have this f sub I, right? Okay. Well, what you see is actually exactly the same thing that you saw in gradient descent. So despite now having even more randomness, which is that for large models, you can actually show that f at xk, so f at your iterates of SGD, will actually converge to a deterministic function. You have the dynamics of SGD completely done. You know exactly the path it takes. Okay. Moreover, what's cool is you can actually analyze this. Okay. And it's completely determined by the spectrum of the Hessian again. That's it. That's all you need. You don't ever have to run SGD ever again. Okay? You just need the spectrum of your data. That's it to appear. Okay. So that's exactly what's going on in this picture. So this is epoch iteration. That's my function values. What I'm doing is I'm just running SGD 10 times, and I'm computing the spread of the SGD runs. Okay, and we can see as I'm increasing n, you can see that it's converging to this red line. This is red line. It's not the mean. I didn't compute the mean. It was what I computed by computing the spectra knowledge. Okay. So I hope you guys are cool. You never have to run SGD, right? That's amazing. All those runs. Saves you a lot of time. All right. What do you need to assume? Well, you basically need to assume the same exact thing. You have to do a little bit extra on your data matrix for SGD. So you again need this sort of funny ratio assumption between n and d. The other thing you need, and this is actually a characteristic again of high dimensional matrices. I wrote down them in a funny form here because this is how random matrix theory people will say. But you actually need something called the delocalization of your eigenvectors. In high dimensions, what this means, what this is actually saying is that your eigenvectors don't tend to concentrate along coordinate axes. So you don't tend to have an eigenvector which looks like 1, 0, 0, 0 in high dimensions. Not so surprising. Any kind of error will cause this to happen. And for most random matrices, this is the case. So for instance, any sample covariance matrix has that property. Will not have it. You can also do something called a random feature. So this is more like neural networks. You can take a random matrix data X, times it by a random matrix W, take a sigmoid of it or any kind of activation function and call that your A. It will also satisfy this property. Okay. That you don't have a delocalization of the eigenvectors. They don't concentrate. Okay. And then you can prove it. So how does SGD work? I mean, this is usually the question that everyone gets. Okay, SGD is much more complicated than gradient descent and any of those. The reasoning is that what actually underlying the dynamics is that there is a stochastic differential equation behind it. And you can write down what this is. So we called it homogenized SGD. It's a stochastic differential equation. So you see you have something that looks like minus grad f, that's like gradient descent, plus a term which has a Brownian motion on it. Okay. This is different than what people have studied at diffusion processes for SGD in the past. Okay. Why is this really different? This is different because what they did in the past is they send their step size to 0. But here we're going to send dimension to infinity. We're going to use high dimensionality to actually give us the result. The other nice thing about this is that you can actually solve this. Make sure I have some time. Okay. And what did we show? We actually showed that this STE is the high dimensional equivalence of SGD. Okay. So what does that mean? It means that if you take any statistic Q, quadratic, then if you look at the iterates of SGD under Q and you look at the iterate of the statistic under the diffusion process, they're actually close in high dimension to make n big. And it actually then turns out that if you look at what happens to this diffusion, this is a random because of the Brownian motion, it will actually converge to its expectation. That one's not as hard to show because of the Brownian motion, we know a lot about its behavior. Okay? So this is actually what's governing that concentration. You have the iterates of SGD are actually converging to some sort of diffusion process, and that diffusion process is actually concentrating around its mean. Okay? And so you can do that, and that's where you get an exact expression for the dynamics of the loss of SGD. So you can show that SGD will concentrate around a deterministic function. So the function value evaluated at the iterates of SGD will concentrate around some value, which happens to be a convolution type Volterra equation. Convolution type Volterra equation, really nice. Probably the nicest thing you can get because they're basically solvable, right? You can write them down. So what this is, what you can actually show is that it has a term which is related to gradient descent. So what you would get if you had run gradient descent, plus the term which is actually SGD. This is what the noise of SGD is doing by generating. You can write down a formula for what it is. It's exactly that term. It's a mixing term. Moreover, all of these quantities only involve eigenvalues of the Hessian. That's it. Really nice. Convolution, Volterra, you can solve it. People here in the audience like, yeah, I know how to solve it. Like everyone has their favorite. I teach a lot of ODEs. So I always make this one as part of their homework assignment. Solve a convolution Volterra equation. It's important. Okay, so let's give a sense of what's going on in terms of convergence and what's happening. So when you have very small step sizes, you see that this mixing term, the term which is generating noise in SGD, that's because you're generating an IKH iteration, actually goes away because it's like gamma squared. So when gamma is really small, your step size small, you don't really generate a lot of noise. You just end up back in gradient descent. That's sort of the thing you expect. Now, when you have very large step sizes, which is actually what you tend to do in practice, you choose very large step sizes, gradient descent is not the term which dominates, your noise is. It's purely the noise which is what you're fighting against. Okay? And that's actually just governing what these pictures are. So now you can understand, all I have to do is compute a spectrum of my matrix, okay? For real data, I plug it into this formula, I can output and I can predict exactly the behavior of SGD at a single iteration. I hope you guys are impressed. Okay, it's cool, right? Like, there's no need to run SGD anymore, right? Like, what all that? I mean, there's still benefits to running SGD because it's fast, but you still have to solve a Volterra equation somewhere along the way, right? Okay, so that might be a trouble, but at least you can do it. You can generally predict it. You can also get some interesting things that you might not know about SGD, because you can study now, you have the exact dynamics of its behavior. You can study what happens. And for those of you who have done Volterra equation before, a lot of you will know that there's something called a Malthusian exponent, or there's this weird crossover where the noise starts to really dominate. Okay, and that's what I'm calling a critical step size. So there turns out that there's this value, which is that once your step size gets too large, the noise becomes the term. It changes the behavior of the dynamics of SGD. When you're below that step size, you just look like gradient descent. That's it. So there's actually a jump. And so that's what you see here as a function of the convergence rate and step size. As all of a sudden this gray line, this is where this critical value is. For step size below, it looks like a straight gradient descent. All of a sudden you see a jump in the behavior of SGD. Its dynamics change. This is a phase transition for SGD with a step size. Kind of fun. Also, if you notice that the best convergence rates actually occur when you choose slightly larger values for your step size. I know some of you out here have probably had to tune. This is why you want to tune a little bit larger. You're actually in the noise regime just a tiny bit. Okay. You can then do the exact same thing and get average case complexity. And for stochastic algorithms, the average case values are way, way better. It explains why SGD just works a lot better than what the theory said, and why we don't even plot the theory a lot of times on our graphs. Your orders of magnitude better. Okay, but we did something more, and I hope there's some stats people out here. Okay, I gave you that you could put any quadratic statistic to measure the homogenized SGD. The diffusion process was close to the iterates of SGD, so you can get dynamics of other statistics beyond the loss. And this is important for statisticians because what they don't care about with SGD, they don't care how the loss is converging. They care about how does the output of SGD do on new data points. You can now write down the dynamics of that. Why? Because you have that diffusion process, which is saving you. So you can write down what those are. So here's the expected risk. So here I'm generating a new data point AB from some distribution, not the distribution that I trained off of, computed as expectation. That's just again just a quadratic. And what you can show is that that quantity has to concentrate, and you can again write down a formula for the exact dynamics of it. So now you have the exact dynamics of expected risk problem. This is all finding this implicit regularization effects for SGD. You can write it down. So what does it look like? What does this term concentrate around? It concentrates around which looks like gradient flow, again, plus some noise term. This noise term is some other function. Okay, I didn't write it down, but it just, again, involves sort of eigenvalue information. That's it. Okay. You get some very simple things. Okay. Hopefully I'm getting rid of some of the ML things by doing these dynamics. The first is that you can see because it just has this gradient flow or gradient descent, what this means is that the expected risk of SGD is always worse than if you adjust from gradient descent. Okay, at least for a least squared. It means that if you had an infinite computational budget, okay, you cannot beat gradient descent with SGD, even though it has noise. A little bit weird. There's no implicit regularization effects of SGD. Okay? The other thing is you can recover gradient flow by either sending the step size gamma to 0 or by making your loss go to 0, because this is the size, this loss. So it recovers gradient to flow in the limit. Okay? So you get pictures like this. You probably have seen these where they go up and they go back down again. Expected loss. Well, here you can see the concentration effect again. So the first is of the training error. The second is the expected loss, and you can expected risk, and you can see you can exactly predict its behavior. That's what I predicted in the red line. Okay. One thing to note is that the loss concentrates a lot faster than the expected risk. Okay, so you have to go much further for N. Okay. You can do this with random features. So this is sort of the neural network version of this. You can also predict exactly the behavior of every single random feature models. You can do this with real data because all you needed was a spectrum. Kind of cool, right? It works. So here are the eigenvalues of MNIST. So MNIST is this data set 0, 4, 1. Here's the training loss where I predicted, and here's the expected risk. Just totally predict the behavior. So this makes this question, hopefully I have a little bit of time, of can you actually go faster? Okay. Can you beat SGD in some way? Okay, so then the next thing, because optimizers and there's all these myths in machine learning, everyone always says use stochastic momentum. Anyone here? Actually, does anyone know that I think in one of the packages, SGD is actually SGD with momentum? Okay, so they lied to you in there. Okay, so stochastic momentum algorithm. So if you've never seen a stochastic momentum, it's very simple. It comes sort of from a physics viewpoint, which is that, well, instead of just moving in the direction of negative gradient, that's kind of current information, why don't I remember where I came from? Okay, so why don't I incorporate that I was moving in some direction from the past? Okay, so that's what's captured in this YK. And then you just do a linear combination of moving in the gradient direction with the direction from your past iterates. Pretty simple, okay? Makes sense, right? Well, it turns out you can do exactly the same thing I did before. There's a diffusion process to write down this dynamics too. Kind of fun. So hopefully I can break some myths in this talk. All right. You can also get under this homogenized SGD a convolution type Volterra equation, same as before, different kernels and things to understand the dynamics of the loss function. That's everything that SGD had. Okay. All right. So if you've ever done momentum, there's probably in one thing that you were taught. What momentum parameter should you use? Anybody? You're at Mila. No? Anyone? Anyone watch Andrew Un's video from like 20 years ago? Nobody had the momentum parameter number? Oh, okay. Well, okay. You're told when I was in school, tells you, I was always told you should just use momentum 0.9. That's it. That was the answer to all problems, 0.9. Okay. Meaning that how much should I weight my path? I just put it 0.9. I kid you not. This was like, it's even built in. You'll hear people still today say, I got to prove that you should just use 0.9. Okay. I don't know why it's there. Okay, so let's look at this and let's try and understand it. So let's see if we can understand what happens if we were to use 0.9 in high dimensions. So here's this stochastic heavy ball. So I'm going to have my momentum and my updates, my iterate update. Okay, so what am I going to do? I'm going to generate a random matrix. I'm just going to output the value of heavy ball at a fixed time. So this is just the function value at the last iterate. And what I'm going to do is I'm going to vary theta and the gamma for my step size, but hold them fixed so that the ratio is some fixed constant. And I'm going to use that constant and run SGD. Okay, because we have exact dynamics, we don't actually have to run any of these algorithms. We could just use the dynamics that we got from the ground truth we know has to be true. And that's what I'm doing here. So the orange line is SGD. The red line is heavy ball, okay, momentum, okay, where I've done it so that the heavy ball using the gamma and theta is the same as using SGD with a different fixed size. Okay, that's all I did. What do you see? Well, you see actually the heavy ball and SGD are exactly the same in high dimensions. They are exactly the same dynamics in high dimensions. You were lied to. 0.9 does nothing. All you did was you scaled your step size in SGD by a certain amount. That's it. That's all you did. You could have used a larger step size is the truth for SGD. It does nothing. Now, it's not entirely true. So you can actually see that you get a little bit faster than SGD, but what you have to do is you have to make your momentum depend on dimension. Okay, 0.9 is not the answer. Okay, not the answer. It's a dimension dependent quantity in order to make this thing work. Okay, and you can exaggerate this effect. You can create an algorithm where you actually exaggerate the effect of momentum by having it now actually depend on dimension. There are some quantities in these algorithms which have to be dimension dependent. And what you get is you can actually get these concentration results. So I always like these just because you don't just predict something is going down and to the right. You actually predict a little squiggly line. It involves sines and cosine. Right? So you can actually predict momentum behavior. Okay. And what you can show is you can actually beat SGD by doing this. So if you actually make your momentum parameter depend on dimension, you can actually get much, much faster. You can not just beat it, okay? In worst case, you'll beat even the worst case values, but you also beat it in the average case. Okay? So you can beat it, but you also need to remember that there's dimensions involved in all of this. Okay. Okay, so here I'm going to end. I know I was a little bit long and hopefully it wasn't too much theory. Again, if you haven't done this, go do a random matrix. You'll be happy. You'll be like, this is amazing. Why have no one told me that if I generate a random matrix that has eigenvalues which look like this? It'd be an amazing fact. What have I shown you? I've shown you a sort of a general framework for analyzing these using random matrices, okay? To somehow get high dimensionality incorporated into our analysis. You can get exact dynamics for these algorithms, okay, which just depend on the spectrum of the Hessian. Okay, and you can analyze this to get things about step size, average case complexity, etc. There's a lot of open problems involving this. Okay, people don't really look at high dimensionality and use random matrices in optimization, use these dynamics. So one thing is like things like, well, what does homogenized SGD actually do in terms of other functions? I just showed you least squares. What are some other models you use? Okay, the big one, which a lot of people don't really know, is what happens if you have heavy tailed distributions for your data. Okay, that can happen. Okay, and then can you get dynamics of other things? So like logistic regression, so these kernel methods. There's been some work on this in gradient flow, analyzing it. And I think the big open question, especially right now for optimizers in general, is, you know, since we're doing neural networks, these are non-convex and non-convex optimization problems. So can we actually devise a framework that actually works for non-convex? Now this is actually tricky because we don't have toy models. We don't have the least squares problem for the non-convex. There isn't one. There's not a nice one out there. Okay, so it involves sort of understanding what are good toy models to work with that mimic neural network behavior. Small versions of something like a least squares, like a quadratic for neural networks. So if people are interested in that, I'm happy to. And then of course, the other question is, can you use this to design new algorithms? Now that you know that you need high dimensions, you can incorporate it through these sort of random matrix universality ideas. Can you design a new algorithm from it? With that in mind. So I just want to say thank you. And this is based off a bunch of works I've been doing. So thank you guys for inviting me. And yeah, forward to talking with you. Any questions? Oh, you want to? No.
Hello? Alrighty, so I guess for starters, thank you for the super cool talk. That was wonderful. And I'll like leave the floor open in case anybody wants to ask any particular questions here. And in the meantime, I have a couple questions that I'm very curious to ask about. So to clarify, you were mentioning at one point that there's no kind of implicit regularization then from the noise in this problem. Do you think that this is just purely a feature then of the nature of the regression least squared problem, and that you do in fact have, presumably in a non-convex problem where you have multiple optima, like local minima, noise is going to be playing some sort of role there.
Yeah, I do think so. I think so because there's no local minima. I think the local minima is the actual effect. But it's not preventing you from overfitting. So I think what this is actually saying is that for even probably non-convex, it's not actually preventing you from an overfitting effect, which is sort of another version of regularization, because you would have seen it here. But it may prevent you, it may help you, the noise help you go to different minimum, local minimum. And so in that regard, that would be some sort of good regularization effect from the noise part. Yeah, it's a good question. Good question. By the way, if anyone has a problem of 2 local minimum, easy to solve, that you can show SGD bounces around, very interested in. That's actually hard to do. No one has one, so it's a good question. Yeah.
Cool. Thanks. So the second kind of question that I was wondering about is, maybe this is going to be a bit of speculation here, but I know these days, of course, a lot of people will be using Atom for large-scale optimization problems. And I was wondering if you could comment on what you think some of the differences and similarity, like if you might be able to gain any insight about something like that from the paradigm that you've explored here.
Yeah, so I think maybe not necessarily Atom, but do people use batch norm here? Anyone know batch norm? Okay, some people. Okay, batch norm is super popular. Okay, I think batch norm can be explained quite a bit through these things. What you have to do, and I glossed over these effects here even, is that we actually have to normalize our matrices. So what this means is that you'll see, like I said, like normalized trace quantities were appearing everywhere. Okay, you need to normalize after every layer in some sense because it accidentally causes large eigenvalues to appear. That's what these sort of normalizations actually do, just generally from a random matrix. You need to do that because from a random matrix theory point of view, you can prove that the largest eigenvalue is going to get really, really large. Okay, without normalizing in dimension. So I think there's some random matrix theory explanations of why you should do things like batch normalization to prevent certain like explosions of things to happen, and it's purely from random matrix theory. Yeah, cool.
Sweet. So actually, on the topic of batch size, or on the topic of batches here, yeah. I guess I was also curious, and perhaps I missed it at one point in the slides, but I was curious to what extent, if any, like batch size plays a role in the results that you've provided here.
Yeah, it actually does quite a bit. So it affects mostly momentum, the biggest. So if you use batches in momentum, what you can show for these types of things is that you don't end up looking like SGD. So there's actually a regime in between, because with momentum, if you use full batch, you're going to actually go faster. Like that's true. So it has to have different dynamics than say gradient descent. So you can actually do the same analysis where you include the batch size in here and see the effect of the transition from looking like exactly like SGD to looking like a momentum, to a pure full batch momentum algorithm. So it's really cool. It's actually quite nice that you can do it. Exact dynamics stuff. So cool.
Very cool.
I think there's a question.
Do we have an extra question? Cool. Alex, would you like to come up here and ask, or just for the people who are online, I'll trade you the mic here.
Sure. It's just a follow-up question of the previous thing about batch normalization.
Yeah.
So if batch normalization or any kind of normalization, layer normalization, whatever, appears to be necessary to avoid like too large eigenvalues, why do we still get good optimization without any normalization?
Yeah, so there's a little bit of batch normalization seems to be used a lot for when things have variance problems, like the variance of your stochastic gradient, so it's problematic in some sense. And I think the normalization is just, so if you have bounded variance, it just means that because of how the data is structured or the architecture, you're not getting this explosion of the largest eigenvalue problem. It's only in some architectures that you're going to get that explosion happening. Okay. Yeah, exactly. It's a little bit of a combination of the data that's going into it and sort of the architecture that's happening. Which is why you don't see it. However, it does suggest one thing is that you should always normalize your thing. So, you should always normalize it. As a good statistician, you should normalize it. So there's that too. And you should get better results if you actually do normalize. Yeah, it's a cool question. Also, I haven't done this. I mean, if you're interested in showing the bachelor thing, I think it's true. I think that it's just a random matrix theory question. Yeah. Oh, go ahead.
Hello, Professor. I'm wondering if this kind of analysis of SGD does apply to exponentiate gradient descent.
We haven't tried.
Okay, yeah.
Yeah, we haven't tried. So there's a bunch of things that we haven't actually done. So,
yeah,
sorry.
The main motivation for this question is because there are some evidence that brain are doing exponential gradient descent, and some synapses distribution is approximately log normal. And if you do exponential gradient descent, it's sort of like you're doing gradient descent in the exponential.
Yeah.
So I'm wondering if this kind of analysis could be applied to other optimization problem that's besides SGD or gradient descent.
It probably does. I haven't we just haven't done
it. Yeah, it's interesting to try, but yeah.
It's definitely interesting to try and use the random, use high dimensionality. If you have a high dimensional data structure, it'll show up. And so
yeah, okay, cool. Thank you.
I see that we're getting
time.
the time, but
Is it time
do we
to
have
go?
any time for any more questions? Or are we wrapping things up right now? Okay. Then I guess we'll have to, so that's it, I think, then for the questions. So if we could just give one round of applause here for Dr. Paquette. And thank you so much for speaking with us today. That was awesome.
Perfect. Thank you. Thank you guys for having me.